Hey, welcome to Pomodoro Joe for Friday, February 17th, 2023. Today we're doing LeetCode problem 783, minimum distance between BST nodes. So BST stands for binary search tree. It's an easy problem. Given the root of a binary search tree, BST, return the minimum difference between the values of any two different nodes in the tree. Pretty straightforward. We have some examples, and then let's look at our constraints. So the number of nodes in the tree is in the range from 2 to 100. So we have at least 2 nodes, but we have no more than 100 nodes. And the node values can range from 0 to 10 to the 5th. So that's a pretty big range. So the straightforward approach would be just say, well, let's gather up all the values of all the nodes and then go through and find all the differences between all those values. I think that might be the approach that we'll take. And one clue to that is looking down here at these constraints. The number of nodes is fewer than 100, which means calculating all the deltas between nodes won't actually take that much time. So that kind of gives me a clue that maybe that's the approach we should take. Okay, so let's put 25 minutes on the Pomodoro timer and get started. So the approach that I'm taking now will be traverse the entire tree, gathering up every single node's value into an array or a set, some data structure. So we find all the values of every single node. Then we will go through every single node and calculate its delta to every other node, and then we will return the minimum difference. Now I might make a small change to that, but we'll start with that as our basic approach. Now how do we traverse the tree to gather up every single node's value? There are two basic approaches. There's the recursive approach and there's the iterative approach. I'll start with the recursive approach. It's simpler to understand. If we need to, we can go to the iterative approach, or if we have more time, maybe I'll show you how to do that. All right, with a recursive approach, let's create a new recursive function here, def. We'll just call it recurse. It'll take some node, and we'll have this return an array of integers. We want to get every single value from every single node. So as with every recursive function, we need our base case. What is the base case? The base case here will be if the node is none. So if not node, then we'll just return an empty list. Otherwise, we will return, let's see, well, we want the recurse on the left node, so that's node.left, and then we'll append that to this node's value, but we wrap it in a list because we need to append these two lists together. And then we'll also recurse down the right node. And that should do it. So now we have a recursive algorithm that will gather up all the different node values. So we can create our list here, and I'll just call it values. And that will equal recurse on our root node. So one thing we could do is we could actually say, for every I in range, for the length of our values, and then for every j in range from I to the length of our values. Actually, we would say I plus 1. We can find the delta, so we can say the delta, and that's going to be the absolute value of our values at I, or j, it doesn't really matter, j, minus values at I. So this will give us a delta for every single value pair, or for every single node pairing. So that's one way we could do this. For me, I think this is like too complicated. Let's just change this to say, let's sort our values. So if we say values.sort, now all of our values are sorted from lowest to highest, so smallest to greatest. And we can just go through once and compare neighbor values. So we can say for I in range, and we'll actually start at 1. So we can compare element 1 to element 0. And we will still go to the length of our values. Now our delta, in this case, will equal the absolute value. Well, we don't even need absolute value anymore because we know that the element at 1 will be greater than the element at 0. So we can say the delta is our values at I minus our values at I minus 1. So this is basically looking at the current value and comparing it to the previous value in our list. Now we can just say our result will equal result, well, the minimum of our result, or this delta. Now, for this to work, I will actually need to have some result to start with, and I will need to set it to something huge. So I can set it to, let's see, our maximum value here, which is 10 to the 5th. Well, I'm just going to set it to infinite because infinite will be definitely higher than anything we'll run across. And at the very end, we can return our result. Seems to work. All right, shall we give this a shot? Let's give it a shot. Why not? Okay, and we pass. Now we only beat 56% of other algorithms for runtime and 32% for memory. Not too bad. Let's see if we can improve upon this. So going back to our initial problem. So looking at our solution here, there are 3 basic components. We have the recursive function that will go through and grab all the nodes' values. We have this sort, which will go through and sort all of the nodes' values. And then we have this iterative loop that will traverse the values, find the minimum delta. So what can we do in here that might improve upon our result? Well, there's one simple thing we can do, and that is if our result is equal to 1, we can't find the smaller result. So we'll just return 1. So in this case, we're just exiting early because we found the smallest possible answer, and there couldn't be anything lower than this. So we'll just return. Let's give that a shot. All right, that makes a significant difference. Bumps us up to 81% for runtime and 74% for memory. That is a huge difference from just one small conditional. One other thing we could do here, so we're calculating this conditional every single time we go through this loop, but we really only need to check if our result changes. Now, unfortunately, because we're using this min here, we don't know if the result changed unless we kept track of the previous result to the new result. But instead of using min, we could actually do our own min calculation by saying if result is less than delta, then we'll set our result equal to delta. And then we'll do the check. So in this case, instead of calling min, we do our own min check here, and we'll only check if the result is 1 if we've set a new result. Let's try that. Sorry about that, folks. I got my conditional in the wrong direction. If the result is greater than delta, so if delta is less than result, then we can set our result to that delta. This should handle it. All right, let's see how much we gain by only doing the conditional when we really need to. And we gain nothing. We actually lose. We go down to 35%. I am shocked by that. This should have been a huge win. Let's try this. Let's just do this. If delta is less than result. Let's do it that way. 81%. Oh man, I was really hoping to beat our 90%. Okay, since this doesn't seem to be giving us too much of a gain, gives us a little bit, but not as much as I was hoping, let's address our recurse. So to calculate our values, we call this recursive function. Now recursive functions are notoriously slow and high memory usage. Not all the time, but oftentimes. So what can we do to replace this recurse? Let's do an iterative solution. Now for the iterative solution, we have a queue of nodes. And we'll start that queue, it's just a list. We'll start it with the root. So we have one node, the root node. Now we'll go through, and while we still have nodes in our queue, we will process them. So while we have a queue, let's just grab the first node. Say node is equal to queue. And we'll pop 0. So that grabs the first node out of the queue. And we'll say if that node, so if we have a node, then we will, well, what do we need? We need the value. So actually I need to have my value store up here. So I'll create a value store. And we'll say our value dot append the node's value. And then we need to do the same for that node's left and that node's right. So we'll just put them in the queue. So we'll just append the node left, and we'll append the node right. And that should give us all the values. We'll push the first node onto the queue. When we pop it out, we'll grab its value, and then we'll push its left and right nodes back into the queue. And if the node is none, if you don't have left or right node, we will bypass it. We'll still pop it out of the queue, but then we won't do anything. It's essentially a no-op. Okay, let's give this a shot. I need to make this called values. There we go. Okay, seems to work. So let's see if we gain anything by removing our recursive. Hey, that is a huge gain. We removed our recursive traversal of the tree, getting the node values, and we replaced it with an iterative solution to get the node values, and we made a huge gain. We beat 92% for runtime and 74% for memory. Now that's pretty darn good. I think that's our winner right there. So here you go, folks. Okay, that's it for me on this one. Hope you enjoyed this. Hope you had fun. Hope you learned something. Hope you can try this one on your own. It's a great problem, really good practice for both recursion and for iterative and for tree traversal. Lots of good stuff to learn with this problem. And it's easy. Okay, hope you enjoyed this. Hope you had fun. Hope you learned something, and I hope you can go out and write better code.